Good morning to all the students. Today we study about signal degradation in optical fiber. Signal degradation on optical fiber due to dispersion and attenuation, intermodal and intramodal dispersion, fabrication of fibers and measurement techniques like OTDR. One of the important property of optical fiber is signal attenuation. It is also known as fiber loss or signal loss. The signal attenuation of fiber determines the maximum distance between transmitter and receiver. The attenuation also determines the number of repeaters required. Maintaining repeater is a costly affair. Another important property of optical fiber is distortion mechanism. As the signal pulse travels along the fiber length, it becomes more broader. After sufficient length, the broad pulses starts overlapping with adjacent pulses. This creates error in the receiver, hence the distortion limits the information carrying capacity of the fiber. Attenuation is a of measure of decay of signal strength or loss of light power that occurs as light pulses propagate through the length of the fiber. In optical fibers, the attenuation is mainly caused by two physical factors, absorption and scattering losses. The rate at which light is absorbed is dependent on the wavelength of the light and the characteristic of particular glass. The attenuation of fiber is governed by the materials from which it is fabricated, the manufacturing process, and the refractive index profile chosen. Attenuation loss is measured in dB per kilometer. Attenuation loss Attenuation loss measured in dB per kilometer. Absorption. Absorption loss is related to the material composition and fabrication process of fiber. Absorption is caused by three different mechanisms. First, absorption by atomic defects in glass composition. Second, extrinsic absorption by impurity atoms in glass mat. Third, intrinsic absorption by basic constraint atom of fiber. Absorption by atomic defects. Atomic defects are imperfections in the atomic structure of the fiber materials such as missing modules, high density clusters of atom groups. These absorption losses are negligible compared with intrinsic and extrinsic losses. The absorption effect is most significant when fiber is exposed to ionizing radiation in nuclear reactor, medical therapies, space missions, etc. Extrinsic absorption. Extrinsic absorption occurs due to electronic transitions between the energy level and because of charge transitions from one ion to another. A major source of attenuation is from transition of metal impurity ions such as iron, chromium, cobalt, and copper. Another major extrinsic loss is caused by absorption due to OH ions impurities dissolved in glass. Next, intrinsic absorption. Intrinsic absorption occurs when material is in absolutely pure state, no density variation and inhomogeneities. Thus, intrinsic absorption sets the fundamental lower limit on absorption for any particular material. Intrinsic absorption results from electronic absorption bands in ultraviolet region and from atomic vibration bands in the near infrared region. The electronic absorption bands are associated with the band gaps of amorphous glass materials. The infrared region above 1.2 micrometer, the optical waveguide loss is determined by presence of the OH ions and inherent IR absorption of the constituent materials. Relay scattering losses. Scattering losses exist in optical fibers because of microscopic variations in the material density and composition. As glass is composed by a randomly connected network of molecules and several oxides, SiO2, GeO2, and P2O5. These are the major cause of compositional structure fluctuation. These two effects results to variation in refractive index and Rayleigh type scattering of light. Radiative loss, bending loss. Here there is a core light ray losses due to curvature and losses caused by an abrupt change in radius of curvature are referred as bending losses. The sharp bend of a fiber causes significant radiative losses, and there is also possibility of mechanical failure. Bending losses represented by this figure. Micro bending. Students, microbending is a loss due to small bending or distortions. This small microbending is not visible. The losses due to this are temperature related, tensile related, or crush related. There is a core and cladding in optical fiber. Signal distortion in optical waveguide. The pulse gets distorted as it travels along the fiber length. Pulse spreading in fiber is referred as dispersion. Dispersion is caused by difference in the propagation times of light rays that takes different paths during the propagation. The light pulses traveling down the fiber encounter dispersion effects. Because of this, the pulse spreads out in time domain. Dispersion limits the information bandwidth. Here, some figures you have to understand dispersion and attenuation in fiber. Group delay. What do you mean by group delay? Consider a fiber cable carrying optical signal equally with various modes, and each mode contains all the spectral components in the wavelength band. All the spectral components travel independently and they observe different time delay and group delay in the direction of propagation. The velocity at which the energy in a pulse travels along the fiber is known as group velocity. Group velocity is given by Vg equal to d omega by d beta. Group delay. Thus, different frequency components in a signal will travel at different group velocities and so will arrive at their destination at different times for digital modulation of carrier. This results in dispersion of pulse, which affects the maximum rate of modulation. Material dispersion. Material dispersion is also called as chromatic dispersion. Material dispersion exists due to change in index of reflection for different wavelengths. A light ray contains components of various wavelengths centered at wavelength lambda 10. The time delay is different for different wavelength components. This results in time dispersion of pulse at the receiving end of fiber. Waveguide dispersion. Waveguide dispersion is caused by the difference in the index of reflection between the core and cladding, resulting in a drag effect between the core and cladding portions of the power. Waveguide dispersion is significant only in fibers carrying fewer than 5 to 10 modes. Since multimode optical fibers carry hundreds of modes, they will not have observable waveguide dispersion. Chromatic dispersion. The combination of material dispersion and waveguide dispersion is called chromatic dispersion. These losses primarily chosen the spectral width of transmitter and choice of correct wavelength. A graph of effective refractive index against wavelength illustrates the effects of material, chromatic, and waveguide dispersion. You can see here there are three types of dispersion: chromatic dispersion, waveguide dispersion, and material dispersion. On the x-axis, we have wavelength in nanometer, and on the y-axis, we have effective refractive index. Effective refractive index is 1.44, 1.45, 1.46, and up to 1.4. The graph of effective refractive index against wavelength showing effects of chromatic waveguide and material dispersion. Model dispersion. As only a certain number of modes can propagate down the fiber. Each of these modes carries the modulation signal and each one is incident on the boundary at a different angle. They will each have their own individual propagation times. The net effect is spreading of pulse. This form of dispersion is called model dispersion. Model dispersion takes place in multimode fibers. It is moderately present in graded index fibers and also almost eliminated in single mode step index fibers. Polarization mode dispersion, pulse broadening in GI fibers. The core refractive index varies radially in case of graded index fibers. Hence, it supports multimode propagation with a low intermodal delay distortion and high data rate over long distance is possible. The higher order modes traveling in outer regions of the core will travel faster than the lower order modes traveling in high refractive index region. If the index profile is carefully controlled, then the transit times of the individual modes will be identical, so eliminating model dispersion. Measurements in optical fiber communication. So, students, now we study about measurements in optical fiber communication. Measurement of dispersion attenuation. Signal attenuation is one of the most important properties of an optical fiber because it mainly determines the maximum repeaterless separation between transmitter and receiver. The distortion mechanism in a fiber causes optical signal pulses to border as they travel along a fiber. When these pulses travel sufficiently far, they eventually overlap with neighboring pulses, creating errors in receiver output. For determining attenuation in fibers, three major techniques are used: cutback technique, insertion loss, OTDR trace. Cutback technique, cutback technique, insertion loss measurement, measurement of insertion loss. In telecommunications, insertion loss is the loss of signal power resulting from the insertion of a device in a transmission line or optical fiber and is usually expressed in dB. If an optical device is inserted into a setup, some of the optical power may be lost in the device or at optical interfaces. Some examples: a fiber connector, a mechanical splice, or a fusion splice may be used to connect two fibers instead of having a single continuous fiber. Some of the optical power will be lost due to non-perfect interfaces, not exactly matching effective mode areas or similar factors. The larger amount of insertion loss may be intentionally inserted in the form of a fiber optic attenuator. A Faraday isolator is inserted after the output of a laser in order to prevent it against back reflections. OTDR, Optical Time Domain Reflectometer. Optical Time Domain Reflectometer. It is an instrument that is used to detect or analyze the scattered or back reflected light through an optical fiber due to impurities and imperfections in the fiber. It is an instrument that is used to detect or analyze the scattered or back reflected light through an optical fiber due to impurities and imperfections in the fiber. An optical time domain reflectometer is test equipment used to evaluate the loss of signal inside an optical fiber by transmitting laser pulses inside the fiber and measures the scattered light signal. The OTDR consists of a high power laser transmitter that sends a pulse of light down the fiber. Back scattered light and reflected light returns to the OTDR through the fiber and is directed to a sensitive receiver through a coupler in OTDR front end. Here you can see operation of OTDR. Here you can see operation of OTDR. Stop. Stop.